You know, there is this very specific sinking feeling that I think every single Linux user has at least once.
Oh, yeah. I know exactly what you're talking about.
It's always late. You've just bought a brand new hard drive, maybe for a media server or, for critical backups. You plug it into the machine, you hear it whir, the little green light blinks, and you look at your screen.
And there's absolutely nothing there.
Nothing. If you're coming from like Windows or a Mac, you're sitting there waiting for that bing. You're waiting for that little icon to pop up.
And Linux just gives you total silence.
It feels broken.
It does. It feels like it's broken, but it's actually a really fundamental philosophical difference. In consumer OCs, storage is just assumed. In Linux, storage is a deliberate act.
A deliberate act. That's a polite way of saying a manual chore. But that whole disconnect, that moment where the hardware is screaming, I'm here, and the OS is going, I've never heard of you. That's exactly what we're fixing today.
We are. We're going to bridge that gap. We're doing a deep dive into the Managing Linux File System slide deck, specifically the 8.6 slides.
Right, and we're not just reading them. We've got the tech docs, but more importantly, we have the quiz bank. And I really want to focus on those quiz questions because they seem to pinpoint exactly where smart people get tripped up.
They highlight the gotchas, the places where the logic just isn't intuitive at first.
So let's set the scene. I want you to visualize a server rack. It's loud, it's cold, we've got a monitor up with this slide deck, and we're just going to click through it slide by slide and really decode this contract between the hardware and the OS. Let's start with slide 1 and 2, the concept bridging the gap.
Okay, so look at the diagram on slide 2. It's basically a split screen. On the left, you've got this drawing of a house.
Okay.
And this house, that's your root file system. Everything from the forward slash on down has rooms, bin, home, var. It's a fully furnished, functional living space.
Got it. I'm with you. The house. And on the right side of the slide.
On the right, just floating in white space, is a box, completely separate. That is your new hard drive. It's got storage, maybe it's formatted, but it is physically and logically outside of the house. It's just sitting in the backyard.
So the problem isn't that the drive is broken. The problem is there's no door.
Exactly. The files on that raw device, let's call it devsdc1 for now, are totally invisible to the directory tree inside that house. You can't walk into the box because it isn't attached to the structure.
And that's where mounting comes in. The slide literally shows a bridge being built between the house and the box.
Mounting is just the word for attaching that floating box to a specific room inside your house. You pick a directory, say emp new disk, and you tell a system, okay, when I walk through this specific door, I want to magically be inside that hard drive.
Now, there is a very bright red warning box at the bottom of slide 2. It says, warning, the mount point must be an empty directory. Why is that so strict? What happens if I pick a room that already has, furniture in it?
This is such a classic beginner mistake, and it causes so much panic. Let's use the analogy. Say you decide to mount your new drive onto a folder called data. But data isn't empty. Maybe you have some old log files in there.
Okay, so there's stuff in the room.
When you mount the new drive to data, you're basically hanging a brand new door right over that existing room. So when you open the door now, you are looking directly into the new hard drive, the old files.
Like a con.
They're trapped behind the wall. And that's the confusing part. They are not deleted. They're just hidden. You've plastered over them. You can't see them. Search tools can't find them. Your backups will miss them. They're just in limbo until you unmount the drive.
That sounds absolutely terrifying. You could have missing data that's just sitting there, invisible.
Precisely. That's why the slide really hammers it home. Always build your bridge to an empty room. Don't wall off your own stuff.
Lesson learned. Empty directories only. Okay, let's move to slide 3. Creating the link of the syntax. We've got a terminal window graphic here.
The syntax is, well, it's pretty straightforward on the surface. It's mount, then what, then where.
The example is mount devs dc1 emmet new disk. But I'm looking at my quiz notes here, and there's a very specific trap related to that first part, the devs dc1.
Yes. This gets so many people. Beginners will often try to run mount devs dc, no number.
Well, yeah, because SDC is the name of the hard drive, right? I bought a drive. I want to mount the drive.
And logic makes sense, but Linux doesn't work that way. See, devsdc is the raw physical rock. It's the entire piece of hardware. But you can't save a file to a raw rock. You save files into a partition, a container formatted on the disk. That's what the number means. SDC1 is partition 1.
So if I try to mount just SDC, it just fails.
It'll throw an error or something like, can't find a valid superblock. It's confused because you're pointing it at the hardware wrapper, not the actual storage bucket inside. You have to target the partition.
That is a crucial distinction. Hardware versus container. Okay, so we type the command correctly. We hit enter. The cursor blinks. And Linux, being Linux, says nothing. So how do we know it worked? That's slide 4, verification.
We have 3 icons on this slide: a list, a pie chart, and a document.
Let's start with the list. That's the mount command again.
Right. If you just type mount with no arguments, it lists everything that's currently attached. But, I mean, have you ever done this?
Yeah, it's a wall of text. It just scrolls and scrolls.
It's awful. It lists every virtual file system, every little system process. It's just very hard to read. That's why I always prefer the second icon, the pie chart. That one represents the df command.
Disk-free.
Close. Disk file system. Yeah, it's usually for checking how much space you have left. But look at the output on the slide. The right-hand column is titled Mounted On. It gives you this clean, readable table. You can see right away, aha, DES-DC1 is mapped to new disk.
Much better. Okay, and the third icon.
That's the document.
Yeah.
It refers to a file.etc. That's the mount table. It's a file the system updates in real time. If you want to know what the kernel truly believes is happening, you can just read that file.
Now, looking at the quiz questions for this, there's a trick question that lists commands to check mounts, and one of the options is FITC.
Ah, the fix trap.
And a lot of people pick it. Why is it wrong?
FIX stands for File System Check. It's a repair tool. Think of it like a surgeon.
Yep.
If you want to know if your friend is in the house, you don't call a surgeon to, cut them open. You call a surgeon when something is broken. Tricks checks for corruption. It doesn't tell you where something is mounted. In fact, running it on a mounted drive can actually destroy your data. It is dangerous.
Good tip. Don't perform surgery just to say hello. Let's flip to slide 5. Removable media standards. This one has some clip art of a tent, and is that a toaster?
I love this slide. It's all about organization. We really have 2 main places we mount things: MELA and media.
And this actually matters for the file system hierarchy standard. This isn't just a suggestion.
Right, the tent represents errant. A tent is temporary. You pitch it, you use it, you take it down. So MRT is for the administrator. If you need to manually mount a drive for a quick fix or to copy some files, you do it in emerent.
And the toaster.
The toaster represents appliances, things that just pop in and out.
Right.
USB sticks, CD-ROMs, DVDs. The standard says these belong in media.
So if I'm running a desktop Linux and I plug in a USB and it just pops up,
it is almost certainly mounted somewhere inside media. That's the designated lane for removable stuff.
I see a command snippet on here that looks a little weird. Mount ISO 9660.
It looks like a secret code, doesn't it? That ST stands for type. And ISO 9660 is the specific file system type for optical media, so CDs and DVDs.
Why do you have to specify that? Doesn't Linux just figure it out?
Usually, yeah. Modern Linux is pretty good at guessing. But optical media is really old tech. Sometimes you have to be explicit and tell the bridge builder, hey, the material coming across this bridge is ISO 9660. You just make sure the data is read correctly.
Okay, so we've got the drive mounted. We see it. We can write to it. But we have a huge problem. Slide 6 and 7 are all about persistence.
This is probably the most critical concept for anyone managing a server. Everything we have done so far, just typing mount in the terminal, is volatile.
Volatile as in, if I reboot, it's gone.
Poof. Vanished.
Yeah. When a Linux server reboots, it wakes up with amnesia. It has no memory of the commands you typed. It only knows what is written in its blueprints.
And the blueprint is the file, etc. stab.
The file system table. If your drive isn't listed in this file, it doesn't exist at boot time. Full stop.
Slide 7 has this exploded view of an entry. It looks like a spreadsheet with 6 columns. I think we need to walk through these because getting one wrong can cause big problems.
Let's do it. Column 1 is device. What are we mounting? Devs DB1, or even better, a UID.
Okay.
Column 2 is the mount point. Where is it going? The directory.
So what and where? That's familiar.
Exactly. Column 3 is the file system type. You have to tell it the language the drive speaks. Is it x4.xfs? Is it swap? Then column 4 is options. This usually just says defaults, but we're going to dig into that next because that's where all the power is.
Right. Then the last 2 are just numbers. Column 5 is dump. This is for an ancient backup utility, honestly. You will almost always set this to 0. We just don't really use it anymore.
And column 6?
That is pass. This sets the order for error checking during boot. Your root drive, the main OS, it gets a 1. It always goes first. Everything else gets a 2.
And if I put 0?
The system just skips checking that drive entirely, which is fine for, non-critical storage.
Okay. There is a quiz scenario about this file that I see gets people all the time. It's the vanishing swap mystery.
Oh, this is a classic.
The scenario is, You create a swap partition. You turn it on, it works great. You reboot the server, and suddenly performance is terrible because the swap is gone.
And the admin is pulling their hair out, checking the partition table, going, but I made the partition. It's right there.
But they forgot the blueprint.
They forgot to add the line to etc. stack.
Exactly.
It doesn't matter if you built the room. If it's not on the blueprint, the OS doesn't open the door when it wakes up.
Let's zoom in on that fourth column options. Slide 8 shows a switchboard graphic. This is where you really customize how the drive behaves.
This is how you secure the system. You have toggles like row for read-only versus a row for read-write. If you have a drive full of archives that should never change, you mount it row, then even root can't accidentally delete a file. The kernel just says no.
I see auto and narrow here too.
That controls whether it mounts automatically at boot.
Why would you ever want no auto? Don't you always want your drives available?
Not always. Imagine a USB backup drive plugged into a server. You don't want that thing mounted 204/7, vulnerable to ransomware or something.
Good point.
So you set it to no auto. Then your backup script runs at 3 a.m., mounts it, does its job, and then unmounts it. It's much more secure.
That's smart. Okay, let's talk about user versus nowser. This is a huge focus in the quiz material.
Yeah, it's confusing because the words are so similar. By default, Linux uses nowser. That means only the root user, the admin, can mount or unmount drives.
Which makes sense on a server. You don't want some random user disconnecting the database.
Right. But think about a workstation. If you have a CD-ROM drive, you don't want to enter the root password just to listen to a music CD. So for that device, you'd add the user option in FISTAB. That lets any regular user mount that specific drive.
So the quiz question asks how to secure a CD-ROM so only root can use it.
Then you would explicitly use nowser. You lock it down.
Okay, so we've edited our blueprint, we saved the file. Slide 9 brings up a really practical problem, the zero downtime slide.
The question is simple. I just changed stab. Do I have to reboot the whole server to apply it?
And rebooting in a corporate environment is a dirty word.
It is. It means downtime. It means alerts firing. You want to avoid it. So after you edit stab, you run the magic command, mount A.
Mount A from mount all.
Basically, yeah. Tells the system, go read the blueprint again right now. If there's anything in there that isn't currently mounted, mount it.
That seems so much safer than rebooting and just hoping it works.
It's not just safer. It's a syntax checker.
Mm-hmm.
If you made a typo in that file, Mountfair will scream at you immediately.
Oh, that's huge.
You want to see that error now
right.
while you're logged in and looking right at it. You do not want to find out you made a typo at 3 a.m. when the server reboots and just hangs because it can't read the config.
That is the pro tip of the day. Always Mountfair to test your work. Okay, so eventually all bridges must come down. Slide 10, dismantling the bridge.
The command is mount.
I want to pause on the spelling. Look at it on the slide. U-M-O-U-N-T. There is no N after the U.
I have been doing this for over 20 years, and I still type unmount sometimes. It is the single most common typo in Linux admin work. It's not English, it's Unix. Mount.
The slide also shows that it accepts either end of the bridge.
Right. You can say mount devsdb2 targeting the device.
Yeah.
Or you can say mount metadata targeting the directory. Linux is smart enough to figure out which link you're trying to break.
But sometimes the link refuses to break. Slide 11 shows this locked box with a big red X. The device is busy error.
Ugh, the bane of my existence. You try to unmount and the system just says, nope, target is busy.
It feels so stubborn. Like a toddler just refusing to let go of a toy.
But you have to see it from the OS's perspective. It's protecting you. If it let you unmount a drive while a program was halfway through writing a file, you would corrupt that file. You'd lose data. So the busy error is a safety lock.
Okay, so how do we find the key? The slide has a checklist. First item, are you inside the directory?
This is the most embarrassing one, and I do it constantly. You're trying to unmount metadata, but your terminal prompt shows you're currently sitting inside netdata. You're standing on the rug you're trying to pull out from under yourself.
So the fix is just
leave. Step out of the room. And try again.
And if that's not it?
Then a process has a file open. A database, a backup script, something is stuck. You need a tool called LSOF List Open Files.
LSOF.
It'll point a finger right at the process. It'll say, process ID 405 is holding this open. Then you can deal with that process.
And the quiz notes are really clear about what doesn't work here.
Yeah. People panic. They try editing the fstab or forcing the unmount. But you can't edit your way out of a busy lock. You have to stop the activity. You have to get the toddler to drop the toy.
Let's move to the last troubleshooting section. Slides 12 and 13 talk about hardware versus logical issues.
Slide 12 is basically the is it plugged in Flowchart. It sounds silly, but if the device file itself, like devdb, doesn't even exist, no mount command will ever work. You need to check fdisk-lu. Does the kernel even see the hardware?
And if fdisk shows nothing.
Then you're walking to the server room to check the cable.
Yeah.
It's a physics problem at that point, not a software problem.
Slide 13 is the logical toolbox. We have a top, DF, and bad blocks.
These are for when the drive is mounted, but just acting weird. DF is for space. Is the disk full? Bad block scans for physical rot. Bad sectors.
Need to top.
A top is amazing for performance. If your server is sluggish, a top will tell you if a specific hard drive is just getting hammered, if the I/O is redlining. Helps you find bottlenecks.
And finally, slide 14, the administrator's quick reference, the cheat sheet.
It just summarizes the whole life cycle. Connect with mount, disconnect with make it permanent with a setter stab, and verify it all with DF.
It really brings us back to that initial idea. This isn't just plug and play, it's a managed relationship. Slide 15 sums it up perfectly. A mounted file system is a contract between the hardware and the OS.
That really is the takeaway. The hardware gives you the potential to capacity, but the OS provides the structure. And you, the admin, you're the lawyer who drafts that contract. You decide. Does it read only? Can users touch it? Does it happen to boot?
And if you draft that contract poorly,
you get data hitting behind doors, servers that hang at boot, or those busy errors that drive you crazy.
Right. You know, speaking of those errors, I really like that perspective on devices busy. It's annoying for sure, but it really is the system doing its job.
It is. We see errors as failures. But in that case, the OS is basically saying, I care more about your data integrity than I care about obeying your command right this second. It's a feature, not a bug.
That's a great thought to leave on. When Linux fights you, it's usually just trying to keep the house from collapsing. Check your blueprints, watch your spelling on a mount, and thanks for listening to this deep dive.
Safe mounting, everyone.